All right, so this time we are going to work on the AC analysis for the differential pair. All right, so the AC model of the differential pair looks like this. The 1 millivolts and this plus minus VGS plus minus, that's VGS1. Here is VGS2. And then PMOS get drain connection, grounded because it's a DC voltage, so which is an AC ground. We explained this last time. Why the DC voltage source is AC ground is because it's literally it's a superposition theory. It's the same thing as when you are using a oscilloscope. You just want to look at the AC signal but not the DC signal. So we remove the DC signal by using the AC coupling option on the scope. So the signal will be brought back to the baseline of 0 volts. It's the same concept. We know the DC offset won't be 0 exactly, but we just try to ignore that, but just analyze the AC signal. So this is a really common method when we are doing AC analysis for integrated circuits. Yeah, just use it. Same here. And there's a PMOS and this is grounded. So this is M3, this is M4. And you're wondering, oh, hey, where is the DC current source? Okay, so in AC analysis, there's no DC component. Okay, forget about that. So for the DC voltage source, you short it to the ground. For DC current source, you disconnect the DC current source branch. Okay, so just remove it. Okay, it's the same theory, same rules when you are doing a Thevenin equivalent circuit, right? You short the DC source and disconnect the AC source. Okay, AC analysis actually is the final purpose. When you are doing the DC analysis in the last lecture, the purpose is to get GM, and the reason you want to know GM is because you need GM to calculate the AC current flows through the channel, and by calculating the resistance of this channel, you times the AC current, you get a voltage gain, the voltage output over here. Okay? Because the final purpose is to, it's maybe for this example, it's not amplifying the AC signal, but however, we need to know how to calculate the output voltage in the AC domain. So when you know AC signal over here, you know what's the output AC signal over here. So you'll know the gain for the AC signal. So that's a total purpose. When you are working on that, I know sometimes it's confusing, it's complicated, but you need to know what's the final goal. So the final goal is to calculate the AC output, not only the current, but also the AC voltage output, so you can find out the voltage gain. So generally, that's the purpose. Okay, so first up, what is GM? GM1 equals to GM2, so which means GM of this transistor, which is M1, and this is M2. So GM of this transistor equals to the GM of this transistor because they have the same DC current in the DC model. So it's setting up the same DC operating points for these two transistors. And these ones equals to this. And times ID. And we derive it in one of the lectures previously. I think it's on Monday's lecture in this week. So refer to that if you don't know where this comes from. And this is also the same as 2 beta n times ID. And we know ID is 20 microamps, and beta n is, we just write it down here. It's 2 times 100 micro times 10/2 times 20 microamps. This one equals to 150 microamps per volt. Okay, and the second one, what is GM3? You'll ask, why do you need GM3? Okay, let's just calculate it. So what is GM3? It is 2 beta P times ID. These are sharing the same 20 microamps in the same branch, the same ID, which is 2 times 40 micro times 30/2 times 20 micro, which is totally 150 microamps per volt as well. So for the third one, you want to calculate for M4, the parameters in M4. What is ID? Because M4 is in child region. It's not is in the linear / child region. Either name works. It's not in saturation. So the ID is equation for ID is different. It's beta n times VSG minus VTHP times VSD minus VSD square over 2. So that's the equation to calculate for, the current, drain current in this M4. And because it's being operated in the linear region, so it's performing like a resistor. And when you are doing this, the derivative of ID over VSD, you're getting beta n VSG minus VTHP minus VSD. Okay, and this equals to what? This equals to R channel, the resistance of the channel, 1 over the resistance of the channel. And further, because VSD is small, right? Because this is being operated in the child region, so VSD is small, so we can totally ignore that. So this equals to beta n times VSG minus VTHP. All right, so that's your the resistance of the channel of M4. Okay, well, this is important. You are asking, why do we need to calculate for that? So keep in mind, after you calculate, you find out the ID over here, the AC component, the AC part of ID is this channel. You just times the resistance, channel resistance of this M4. You can get the voltage directly because this is ground, AC ground. So the current times the resistance, you can directly get VL. So that's why you need this. Critical. Okay, so now let's calculate for that. So RCH equals to what? Equals to 1 over beta n. Actually, it's beta P. Sorry, beta P. Beta P. The P moles. Beta P times VSG minus VTHP, which is 1 over 40 microamps per volt times 30/2 times 5 minus 0.9. So if you do a calculation, you can find out this actually equals to 407 ohms. Okay. So now, what about M3? Do we calculate for M3? So we know the GM of M3. And there's another special property for M3. If you look at that, the structure, it has a gate-drain connection, okay? So which means VSG3 equals to VSD3, okay? And we know that GM times VSG equals to ID. Okay, so ID is the AC current oscillating in the channel. Okay, and we know that here's the equation. So because this equal to this, because they are being shorted together, so we know that ID3 also equals to GM3 times VSD3. Okay, because VSD is the voltage drop across these 2 points, which is actually the channel of the transistor. Because in the PMOS, I know you have this connection, but the thing is the PMOS is also has a channel, right? Whatever NMOS or PMOS it is, it has a channel, and that's N well. So it has a channel, and the voltage across these two terminals, the voltage drop across these two terminals, divided by the current, which is ID, which equals to the resistance of the equivalent resistance of the channel. So when you have a gate drain connection, you can use this equation to find out the channel resistance of the PMOS. Gate, drain, when the gate and drain are connected. When the gate and drain are connected, we can find the channel resistance of the PMOS, which is, look at here, VSD3 over ID3 equals to 1 over GM3. So this transistor performs like a resistor with a resistance of 1 over GM3. So there's no difference for this part compared to this, and the resistance is 1 over GM3. All right, keep in mind. And next, number 4. Since we already know all the GMs for every single transistor, so now is the time to calculate ID. So ID is AC ID, right? So if you draw it, let's assume this is ID1, this is ID2, and both of these two IDs are from top to bottom, okay? And you're asking why you don't draw the top part. So, I mean, for this part, it's just a resistor, right? Which is, you don't have to, you can draw it if you like, but it's the same AC current oscillating in the same channel, just one channel, same current. We assign the polarity of the AC current from top to bottom to be positive for ID1, and for ID2 also from top to bottom is positive. This really matters because actually the AC current is oscillating. Sometimes it's going to go up, sometimes it's going down. But you need to specify a direction for the AC current to be positive first in order to make the calculation correct. So that's the AC current flowing in this branch because that is a common ground from here to here. So actually the AC current is flowing because this is the AC source, right? It's flowing to here and go back here and come back here and come back, go back to the ground. So it actually works like this. It's oscillating in this circle. Okay, so it's going back and forth in this circle, actually. So ID1 in that case, so ID1, for example, is going like this, right? ID1 is going there. It's just one current because it's just one branch, one circle here. ID1 is going like this and then going back, going upward. So ID1 is actually equals to minus ID2. But however, GM1 equals to GM2 because this one is not a vector, it's just a number. You can find out is actually VGS1 equals to minus VGS2. Why? Because ID equals to GMVGS. Okay, so you can get this conclusion over here. And now, what's next? You do a KVL for this circle. So starting from here, it's plus minus for this AC signal. So starting from here, start traveling. So it will be minus 1 millivolt plus minus, so it's VGS1, and plus minus, so it's going to be no, following this branch. So it's minus plus, and then go back, right? So it should be minus VGS2 equals to 0. So that's a KVL for this circle. And further, you can find out minus 1 millivolt equals to VGS2 minus VGS1. And combine with this one, and you can find out minus 1 millivolt is actually equals to VGS 2 minus VGS1, which is minus VGS2, which is 2 VGS2. And further, VGS2 equals to minus 0.5 millivolts. All right, and which equals to, and also VGS1 equals to 0.5 millivolts. They are equal and opposite to each other. So good news, we know VGS now. Okay, so what's next? So now we know VGS, all this VGS. What's next step? What's the next step? Calculating for IDs, because VGS ID equals to GM VDS, and you know GMs, you know VGS. Just calculate IDs. If you know IDs, and you know the resistance over here, the channel resistance, you can directly get VL. Okay, now let's find out IDs. Since we know VGS and ID1 equals to minus ID2 equals to GM VGS equals 150 microamps per volt times 0.5 millivolts, which is 75 nanoamps. So this is just a number. It's oscillating all the time. So sometimes it's negative, sometimes it's positive. This is an AC signal. But never mind, we just calculate the amplitude for now because we only care about the amplitude for the voltage gain. So overall, AC plus DC for the entire circuit. ID1, keep in mind, I'm using lowercase I but uppercase D, which means it's the AC and DC signal combined together, which is 20 microamps plus 75 nanoamps, which is 20, this is nano, okay, 20.075. No, we cannot do that because this one is a sine wave. We cannot directly add to it, right? So it's going to be a time variant signal. So actually, you couldn't do this. It should be ID1 equals to 20 microamps, which is the DC current, plus 0.075 sine 2 pi ft. So that's a sine wave. This is for M1 and M3. And overall AC plus DC for M2 and M4 will be ID2, which is 20 microamps minus 75 nanoamps, which is actually 20 microamps minus 0.075 sine 2 pi ft. Okay. So now what is VD? You know IDs already. What is VD? You need to find out VD, which is actually V out over here, because you know the R channel of this transistor. So actually this part is equivalent to this, and this is R channel. So if you do that over here on this paper, it looks like this. Okay. We just drew the right part, the right half. And this is our channel, and this is V out, and that's your ID. It's oscillating back and forth. It's the AC signal. Okay, definitely you can find out V out because it's just Ohm's law, right? Just ID times RCH. So your V out equals to what? AC wise equals to ID times actually ID2 times RCH. So which is 75 nanoamps times what? 407, which is 0.07 millivolts for the final result. And if you want to verify this, which is part of the homework, what you want to verify is the V out. Right? If you have a circuit connected in your device, something like this, it's a little math, right? You can run it. Oh, where's the model? Yeah, I should actually change the models. All right, run and test your V out. So here's a V out sine wave. So here's a problem you need to pay attention with. So the sine wave over here, if you probe it, you can see that you define 1 millivolts as for the amplitude, but actually the peak-to-peak voltage is going to be 2 millivolts. So the 1 millivolt over here is actually the amplitude, which is from the baseline to the peak. But however, the peak-to-peak voltage is actually 2 millivolts. Keep in mind. So now you know your input peak-to-peak is 2 millivolts. And so let's look at the V out. What is the V out peak-to-peak? So the V out peak-to-peak is 73 microvolts. But however, in our example, what we just calculate on the paper, we are using 1 millivolt as the input for all these calculations. So if you want to just make it easier, we can directly just change the amplitude to be 0.5 to make the peak-to-peak to be 1 millivolts. Okay, and now let's measure the peak-to-peak voltage for the output. So it's negative 30, or the amplitude for the absolute value is 36 microvolts. And if you look at the calculation we have, I think it's something around 30 microvolts. So this is verified. It's pretty close, and the calculation, the simulation matches. So this is how you do this homework. And I don't think you still need the demonstration for 4.7, the problem 4.7 in the homework assignments. It's just very simple PMOS. You just do whatever I did in the example. I have a simulation schematic in the homework assignments package. So just repeat that work and show the calculation matches with your simulation, matches with your calculation, and you are done for this homework assignments. So 2 problems: the PMOS simulation and also the differential pair. You want to repeat all these calculations I did today for this lecture and the one I did last time on Wednesday, that lecture. So both DC and AC analysis plus a simulation, okay, demonstrate that works on our side. All right, this is pretty much everything for DC and AC analysis for this CMOS transistors. And we're going to start with current meters tool, which is being used for setting up the voltage references for the integrated circuits. We are going to start the lectures next week, and I will see you in the future lectures.